set the stage on Monday with Dr. Avery talking about the atmosphere, the environment. And presumably you're already a little bit familiar with that. You know, being able to figure out what pressure, temperature, density is at altitude, because those are going to be really important for determining your actual aircraft characteristics, your operating environment. And pretty much everything we learn in here can be applied to any fluid. You just have to know what those properties are. So whether it is a gas or whether it's a liquid. So when you hydroplanes for a submarine, for example, everything we're learning about wings in here can be applied to that same situation. Sails on a boat, right? So it doesn't really matter. So you need to make sure that when you're going over what we're learning in class, that you don't try to pigeonhole it and say, no, it's only about aircraft, right? It's fairly expansive. So as an example, so I was at Sandia Monday and yesterday, and I just flew back on the 1:30 flight coming in. It's not. But so Dr. Elving and I were flying out of Stillwater Monday morning. Beautiful day here. So we were socked in until about 11. So the plane's supposed to take off at 6:30. All because this is what Dallas looked like. From about 5 in the morning to around 11, which is when it finally started to clear. And I think this is really pretty amazing. So someone just happened to be taken off at times, so there were a few planes that were going out. They were really limited from the operations side because ATC was essentially under VFR, IFR conditions in this case. So they, you can look at this and see the skyline and immediately know which way the wind is blowing. Right? So this is just a giant boundary layer is all this is. So stuff we learned about in fluid mechanics a little bit last semester, and we learned a little bit more about this semester. So you can see it flowing in, going to protuberances, kind of laminar up here, and then becomes turbulent when it hits that urban area. And it was interesting because one of the things that we're going out to talk about was developing systems for UAVs and urban air mobility, Uber air taxis and the like, to fly in this kind of environment. And one of the unknowns as well, what happens when you say fly behind a building? Because the wind environment is really difficult to predict. So another thing I thought was be interesting to share. I thought I had a movie in here, but I don't see it. But we'll just pull this up because this is actually the real reason for our trip, was to talk about these things, because we're starting a project with Sandia and JPL to build these things, which are solar balloons, very simple systems, but they're really kind of neat when you think about what you talked about on Monday, because all this is, I think you're in here, Reed, right? These pictures. And I thought I had a movie, but trying to get an idea. I like this picture from here. It's better if we had the video to show. But this is just a slug of air. That's all it is. Slightly warmer than the air outside, the ambient air. Just being heated up by the fact that this is dark, sun comes in, heats up the air on the inside. It heats it up on the inside. What's going to happen? Why does it go up? Density drops, right? Because density is a function of the temperature. And this happens all the time. And this is what causes thunderstorms in Oklahoma. You're waiting for this slug of air sitting somewhere out in, the western part of Oklahoma, or you can blame the Texas Panhandle, right? So it's just a big slug of air sitting there, slightly warmer, but with a lot of humidity in there, so that provides a lot of energy. So it heats up, it's slightly buoyant, goes up into the atmosphere, and the next thing you know, you have a big thunderstorm or potentially a supercell that starts moving over the winds off to the west, from the west and east, and that's what we get in terms of a thunderstorm. So one of the reasons I like this is you can actually, you see this in helium balloons as well, called zero pressure balloons, which is basically just a big floppy plastic bag. You put it in there and you can kind of see the shape of that gas as it's sitting there at the top. And as it moves up to the atmosphere, all it does is expand, as you would expect it to. As the ambient density is dropping, ambient pressure is dropping, that initial volume of helium that you started off with, right, that mass that you started off with stays the same, and it just fills up, it just expands to fill the container that it's in as the pressure drops. So anyway, I thought that was at least relevant to some of the stuff that you talked about on Monday. So before we go any further, let's talk about the homework real quick. Because we do have, which you'll notice on this homework this week, a little bit more of what you had last week. So you're actually repeating some of the problems, it's just a slightly different change in the parameters. So you should be getting really intimate with X-foil. Get to know it. So, you know, two of the problems you did last week and then the problem that you're doing this week. But just, again, rehash. It's stuff you've already done, right? So it's just making sure you remember what you learned last semester in terms of setting up what lift and drag curves look like. But really now applying this practical application. Because more often than not, you know, unless you're designing an airfoil, your aerodynamicist, you say, I'm going to take it into the wind tunnel and measure it. If you're designing an aircraft, you're going to do one of two things. You're going to go to a book and look up a bunch of lift curves and pick out one that you think is going to work. Or, more often than not, you're going to go to a program like X-foil, and could even be X-foil, depending on what regime that you're designing for, and using that to analyze a variety of different airfoils. It's exactly the process you go through, you know, if you're designing a full-scale airliner. You know, you start going through and looking at different candidate airfoils and figure out which one of those is going to be best. So, goes back to one of the things we're going to ask continuously throughout the semester. We're always going to be thinking about performance. In this case, what is best in terms of an airfoil? The right answer is always, it depends, right? It depends on what you're looking for in that particular airfoil. There are lots of parameters, right? Obviously you think, oh yeah, I want it to be low drag. That may not be the driving parameter. Typically, you're going to be looking for high lift over drag ratio. That's going to be your driving parameter, and that's why the drag polar is so important to us, because it plots both lift and drag, and the shape of it tells us a lot about what's happening with the airfoil. We'll go back and remind ourselves about that. The other piece is that lift curve slope, which tells us stuff like, oh, maximum lift coefficient. That's great when you want to know what your stall angle of attack is. That's typically not where we're going to be operating at. We're going to be operating somewhere down in that cruise lift coefficient where we're performing at maximum lift to drag ratio. Lower lift coefficient, lower drag coefficient, and that's our highest lift to drag ratio. So in this case, part of this is to get you familiar with loading up airfoils, because these NACA airfoils that we have here, they're great, you know, for to start off, but they can only take you so far. You know, they're essentially over 100 years old, some of them. So, you know, we want to use something a little more modern. So these airfoils here kind of give us a better buffet to choose from based upon what we want to be able to optimize for our particular aircraft. So some of this is going to be based purely on aerodynamics, some of it's going to be based upon structure. Sometimes one of the driving parameters is going to be the thickness of your airfoil, because you need to have a lot of mass inside. Maybe you need to have a big spar to carry weight, maybe you need a big area to carry fuel, maybe you need someplace to put your landing gear. So those all could drive this design of your airfoil outside of purely aerodynamics. So you got to compromise with the other design drivers. So the other piece of this is your team problems, right? And so you're going to see these pretty much every week. And the idea, again, behind these is first you did this individually last week. Now you meet with your team. You start comparing notes. You say, oh, what did you get on this team problem? What did you get on this? And so this is your opportunity to share that. And then essentially either choose the best or really concatenate a bunch of these and say, well, take some of this, a little bit of A, a little bit of B, put it together. So that becomes your submission for your team. So you have one team submission for each team problem. Right? We'll actually set up folders. I don't think we've done that yet, so we'll have that for each of the teams in here, so that we can see it correctly. So yeah, you will utilize these in your progress report and in your final report. So this is not only just to help you facilitate discussion on your team, but get some of the work out there. So that way you're not doing this at the last minute. You're already going to have this in your back pocket so that we can start putting it into the report. Okay. Any questions about either of these before we get started? Okay. All right. So we can talk about some more when this comes up. All right. Now, this is going to be kind of a driving concept behind a lot of the stuff that we're going to do. So as I mentioned before, we're going to spend some time talking about the science of aerodynamics and aeronautics, and then we're going to come back and talk about aircraft design. What we'll see when we go back and forth between these two things is, we just talk about designing airflow, for example, that's usually really not where you start. And that's where the Wright brothers started, where they went back and said, let's, look at different airflow characteristics, because they didn't know. They had no idea what the possibilities were in terms of selecting airfoils, and what airfoils would do what. But we do know, we have an idea, because we have all these airfoils that we can pull out of the book. And so we have a good idea that we'll have airfoils that have high lift drag ratio, that have really low cruise drag coefficient, that have really high lift coefficient. So we know those are already there, and we could say, well, I'm just going to design my aircraft knowing that I can go and pick an airflow layer. So you don't have to go through that process. And we do that primarily through these problems right here, which are benchmarking problems, right? And that's where you should be at in your design right now, going out and looking at all the other options that other people have already done. They've done the work. Your design has to be able to at least be as good, if not better, than the other solutions that are already there. Because if it's not, then what's the point of going through that process? So you want to be able to see what's out there, not only to jumpstart your design, but also to make sure that your design is going to be better. Okay. So if you have questions about the design process as we go through, we'll come back and remind ourselves about that. So I'm going to go through these pretty quickly, because you've already seen a lot of this before, but it is helpful to kind of remind yourself, since you have like a whole Christmas stuff over, holiday, and you ate a lot, and you just kind of gets flushed out of your brain. So, conservation of mass, conservation of momentum, combine them together. Hey, look, you get Bernoulli's equation. Great, right? That's all you'll see of this. So, actually, we'll come back and revisit this a little bit later, just because it's kind of fun. And we'll turn this into like a vorticity, because that's really where the stuff from X-foil and how we predict airfoil characteristics come from. But kind of the most important one is this really simple equation, again, that you learned back in fluid mechanics, which, if you think about it, essentially relates the amount of energy that you have in a bundle of air. So you have this pressure energy, you have this kinetic energy, and then you have this potential energy. And you're keeping that energy constant for that particular parcel of air as it moves through the fluid. You can change one for another, but you're always keeping it constant. Now, this becomes important in a couple different ways, not only for how we predict what's going on in airfoil, but also how we, measure pressure and how we talk about pressure. Because when we think about pressure, say, in this environment in here, we're thinking about the atmospheric pressure. That's actually the static pressure. But whenever we have a fluid that's moving, we also have the dynamic pressure associated with it. And we call this thing Q. And we typically, when we're, say, for example, looking at wind tunnel tests, we don't think about it in terms of velocity. Velocity is not as important as the overall dynamic pressure, because it's these two things that are important, the density and the velocity that you're operating at. What is your value of Q? And we'll often have here aerodynamicists talk about that. What's the Q value? And hear this all the time. Anyone ever heard the term max Q? Where you hear that from?
Rocket launches.
Rocket launches. Why? Because this is your most dangerous point. And guess what? It doesn't happen when you're going the fastest, right? Because when you look at the value, velocity is going up, and you start off going really, really slow in your rocket, your large rocket, right? And then you're accelerating as you go higher and higher up to your orbital velocity, but your density is dropping exponentially. So you have some peak value in there, right? And so that's going to be your maximum dynamic pressure. That's the part that you're designing for. If you're looking at the aerodynamic loads on your rocket and your airframe, your fairing, that's what you're designing for with this piece right here, because those are the forces actually acting in the rocket. Now, we can utilize this in lots of different ways. We'll come back and talk about this for measuring airspeed. And so our basic pitot probe operation, just goes back to this simple equation right here. Now, for the most part, we're going to be focused in the near term on this thing, on the wing, and so we'll remind ourselves about the different pieces that we have here. First is the span, tip to tip, so that's just a geometric definition. Span is one value, you're going to have one number for that. And then we're going to have the chord, and the chord is going to go from the leading edge to the trailing edge of the airfoil. And that most likely will vary as you go from one wingtip to the other wingtip for your aircraft. If you have a rectangular wing, what's known as a Hirschenberg wing, that C is constant as you go across. But again, more often than not, your wing is going to vary, either for aerodynamic reasons or for structural reasons, or typically a combination of both of these. And then, of course, we have our wing area, which is a combination of those. Now, all three of these become pretty important when we start to talk about three-dimensional aerodynamics, and we bundle all of those together with our aspect ratio. Aspect ratio goes to infinity. In that case, when our aspect ratio is infinite, then that approximates our two-dimensional airfoil characteristics. Okay? Now, we do have to make sure that we're talking about the right thing. When we say the word airfoil, we're always meaning that two-dimensional cross-section. Something like X-foil is only looking at calculations about that two-dimensional profile that you have. It's assuming that you have no flow in this direction along the span. There's no span-wise flow, because as far as X-foil is concerned, there is no span-wise dimension. It lives in a two-dimensional universe. Whenever we mention the wing, however, we intrinsically mean that that's a three-dimensional construct. Both of these are important. Like I mentioned, a lot of times what we'll do when we're designing an aircraft, we come in, we design the wing first, and then we come back and select an airfoil. So once we have an overall shape of the wing, knowing that we can probably, most likely, pick out an airfoil that's going to meet our characteristics. But you can also go the other direction, choose an airfoil first, and then design the wing about it. Okay? There's really no right way or wrong way, it really just depends upon the approach that you take. Now, to remind ourselves then about the definitions of our dimensionless coefficients, we have a lot of these, but the three primary ones that we're going to deal with are lift coefficient, drag coefficient, and moment coefficient. And we define these first in a three-dimensional fashion. This is not only how we did it traditionally and historically, but this is the more practical approach, because that's what we want to be able to get, is define that, right? So our lift coefficient is a definition based upon how much lift your wing is generating at a given dynamic pressure for a given area. Likewise for drag and for moment. Right? And remember, these are dimensionless values. And why do we non-dimensionalize them? So that when we're sticking these in a wind tunnel, we only have to do the test once. Add a given Reynolds number, a given Mach number. Once I have it for that given geometry, I'm done. I don't have to come back and redo that test if I scale my wing up or down, as long as I'm matching my other dimensionless parameters on which these depend. Now, from this then, you can extend these to the two-dimensional world. And all you're doing, if you notice here, you're talking about lift per unit span, drag per unit span, and moment per unit span. Where did your S go down here? Well, it's just V times C. Because in a two-dimensional world, when you're extruding your airfoil out, it's going to be at a constant chord value. Right? It's the only way it can go. It doesn't know how to do anything else. Right? So this then brings us, once we have these basic parameters, to start thinking about the overall design and shape of the airfoil. What we do know is airfoils all kind of have the similar characteristics in terms of, hey, I'm curvy up here, I'm sharp back here, I kind of have this flat area. Those are all there for a reason. This is primarily to provide your overall surface length for your lift. However, you may think about this as, well, S, right? I need a really big S for my lift. Well, most of your lift is actually happening right up here, okay? Because that's where the pressure is acting at. The rest of this is really to decelerate your flow in a way such that you're doing it at minimum drag coefficient. So that gives you the lift that you're looking for. That's kind of your ingoing design value, because in cruise flight you'll say, well, I want my lift to be equal to weight, so I have to generate so much lift. So I'm looking for that number, but I want to do it at a minimum drag value. So that way I have a maximum drag ratio. And that's where the whole shape of our airfoil, basic airfoil comes from. Okay? Now in this case we can see our flows attached. We'll look at lots of different cases where flow is attached and not attached. Okay? Now, why is it shaped like it is? Well, as I mentioned, it's so that we can accelerate air pretty quickly here. When we accelerate the air, we're dropping the pressure from that Bernoulli's equation. I'm starting off with P plus 1/2 rho V squared. If I can accelerate V, then my pressure is going to drop. Now I have a pressure force acting in this direction. Okay? So all of our kind of airfoil geometry is based around that. So when you're going into X-foil, for example, you know, you can design your airfoil specifically by looking at things such as chord, leading camber line, your camber value, and your overall thickness, leading edge radius, trailing edge radius. So you can actually go in and look at options for this in the future where you can change the values. You can start off like something like a NACA 0012, go to the geometry design menu and say, hey, I want to change my leading edge radius, or I want to change my trailing edge. I want to add a flat to it. And those are all things that are very, very easy to do in something like that, in X-foil. Now, we do have to be really careful with this, because I mentioned the Bernoulli equation, and it's an essential way that we can use this to define how lift is generated on airfoil. But we have to be careful in terms of the cause and effect on this. And this is a very common trap that people fall into. So let's think about this in terms of our airflow moving around the airflow. Let's say it's attached, so I don't have to worry about separated flow in this case. I have two parcels of fluid here, one on the top, one on the bottom. As I move over, what's going to happen to those parcels? Well, I had this kind of longer curvy shape